All right. We're starting lesson 11.4 at the start of this week, and here's a few things you need to know. It's all about the angle's location. When I say that this whole week, you're going to hear me go, where's the vertex? Where's the vertex of the angle? Remember, the vertex of an angle is just where the two sides intersect, correct? So we're going to use that over and over again all week long. By the time Friday afternoon hits, you're going to be tired of me asking you, well, where's the vertex? Okay? So this is one of those times, if you memorize early, I won't ask it as much, all right? So make sure you have this down. These are one of those things where, let me just kind of be a precursor. I have jokingly called this worksheet I give every time I teach this unit, the circle of death, because it has 40 different angles on a circle. I think I might change it to circle of doom, just so it doesn't sound quite so depressing, but you know, it's still pretty bad. Most people survive it and do great on it, but it's one of those things where it's just gonna be very overwhelming, and this is the start of it. This is the stuff that you would have to know. Are you guys ready? All right, so first things first, let's get our definitions down that we need. And the first one is called an inscribed angle. Now remember some terminology that we used before. Inscribed is when either the circle or the polygon is located where? Inside. So when I have an inscribed angle, guess where the angle is going to be located? Inside the circle. So an inscribed angle is an angle whose vertex is on the circle and whose sides contain chords of the circle. So maybe this is a little bit easier way for some of you to memorize. It's basically where the two chords are going to intersect on the circle. So it's really this angle right here is always your inscribed angle. So just think about infinite number of inscribed angles you're going to be able to form. So we're going to be using a lot of those, but look where the vertex is. The vertex is on the circle. Also, we have the term, and I used this last week with you, but not a lot, the term intercepted arc. Okay, an intercepted arc consists of all the points that lie on the sides of an inscribed angle and all the points of the circle between them. So let me explain it like this. An intercepted arc is basically if you were to extend your angle and you were to cover it up so that way you couldn't see anything else, what would be left? This part of the arc. So that's called the intercepted arc. It's where the sides of the chords intersected. So that's why it's called intercepted. It's kind of like the idea of football. You intersect something, you're in an intersection of it. So intercepted arc, we're going to use that terminology a lot because the relationships between angles and their intercepted arcs. Guys, you've already used it. Okay? When I draw a circle like this, and I say this is the center, and I go, all right, here's A, B, C. Is that a central angle? What is the central angle's intercepted arc? Yeah, it's going to be arc AC. We've already been using that because we know the intercepted arc and the central angle have the same degree measure. So we've actually been naturally using that concept. All right, we have another term too, and it's subtends. Aren't you like the fancy word? Chord or an arc subtends an angle if its endpoints lie on the sides of the angle. So the idea of it right here is we know that if I go from here to here, here's my endpoints of my angle, DF subtends angle DEF. Or in that little circle I had originally to the right, if I had this, and we had arc AB here, arc AB subtends that central angle. So basically, when we talk about the arc first, it subtends the angle. If you talk about the angle first, it intercepts the arc. So it's an intercepted arc. It just matters which direction you're going. So just know they're going to use terms both ways. They're just using the fancy geometry terms. I like intercepted arc the most. Probably. And well, obviously I use inscribed angle comments all the time. So what are some of our theorems that we're going to be working with on this? This will not let me scroll. Here we go. We'll just do it that way. All right. An inscribed angle. Okay. So what is the rule? It says the following. If I have an inscribed angle theorem, the measure of an inscribed angle is half the measure of its intercepted arc. It's half the measure of its intercepted arc, which means the following. If I'm looking for the measure of angle ABC on any of these scenarios, all I ever have to do is take half of the degree measure of its arc. So in this case, see if I can get to go a little bit wider. It doesn't work. So don't let me enlarge either. What a good day. Love how my pen settings change right in the middle of doing a video stuff. All right, so here's the thing. I want to see how logical this looks to you guys. Let's think about this for a moment. What if I drew a central angle that intercepts arc AC? Now guys, look at the measure of this angle compared to this one. Which one's bigger? The central angle one. Think about it. The closer you get with the vertex, isn't it wider and wider the angle would have to be? So obviously, at least we understand the inscribed angle, its vertex is further away, and the further and further away you're away from the arc, when it narrow and narrow it becomes. So it's gonna be smaller. Now, here's the cool part about it. What if I know the measure of the angle? Can I find the measure of the arc? So couldn't I also go 2 times the measure of angle ABC is equal to the measure of arc AC? Could I go both ways with this? And the answer is, of course. Because we can be able to do the math pretty simply. All right, so looking at this, let's look at the first one. You have to be really good at figuring out which arcs and which angles go together. So which intercepted arcs go with which angle and which angle subtends, that type of stuff. So let's look at the first one. It says, find the measure of angle PRU. So I'm looking at this first one. I'm looking for this angle. Okay, now guys, here's my question. What is that angle's intercepted arc? Yeah, arc PU. Well, where's the vertex of that angle located? You always ask yourself this. Where's the vertex located? On the circle. So it must be an inscribed angle. So what are we going to do? To find its measure, the rule says I have to find half of its intercepted arc. So we know the measure of angle PRU is 1/2 the measure of arc PU. So that's going to be 1/2 of 118 degrees. What's that going to be, guys? 50 what? 59 degrees, right? Ugh, love how this is not scrolling. Oh, well. I know, that's almost too easy, isn't it? Look at the next one. It says, find the measure of arc SP. Now, if I look for it this time, I'm like, okay, here's my arc. I want to know its measure. Well, then you see, all right, what angle does it subtends? All right, which angle helps form it? Well, guys, what angle helps form arc PS? Yeah, angle PRS. Well, aren't we going to use the relationship that if I double the angle, I'll know the arc? Right? Yeah, because remember, the angle's half the arc, so I should be able to go the opposite way. So with that, we know the measure of arc SP is going to be twice the measure of the inscribed angle, PRS. So it's just 2 times 27. It's 54 degrees. What do you guys think? Easy? Good, let's keep making it easy. Now, don't get me wrong, it gets more complicated, but at least at the beginning it's easy to understand. Because the more diagrams I throw in there, more chords and all that type of stuff, the more it's going to look nuts. You have to be more discerning. All right, on this first one, it says, find the measure of arc ADC. So I want to know the measure of arc ADC. So I'm going from A all the way around here to C. Any suggestions on how I should solve this one? Which one? Yeah, so yeah, I'm looking for the measure of arc ADC. I need to go twice the measure of my angle ABC, because I know the angle measurement, and this is the angle that forms my larger arc. So all I have to do is go 2 times 135 degrees, and that's 270 degrees. In my head, that makes sense because that looked like a major arc anyway, and we know major arcs have to be greater than 180, so kind of logical when we work with that one. All right, how about the next one? I want to know, this time, the measure of angle DAE. Guys, what do? I want to know that angle. Yeah, it's just 76 divided by 2, because it's 1/2 the measure of arc DE. So it's just 1/2 of 76 degrees, which is going to be in what, 38? Yeah, it's supposed to be that easy. Now, could you always throw algebra stuff in there, like have variables in both the angle and the arc or something like that? Yeah, but it's still the math rules hold the same. Hopefully you guys are starting to get that in mathematics. Is like, just because it looks goofy doesn't mean the rules change, right? You can still use the rules. All right, next one, guys. I want to talk to you about the common sense theorem right here. It says the following. If inscribed angles of a circle intercept the same arc, or are subtended by the same corridor arc, then the angles are congruent. Now, what in the world we're talking about? All right, guys, look at your hypothesis there. We have arc AB. It's there in gold, so I'm going to highlight it in yellow. Does that subtend 3 different inscribed angles? Those are all done in different colors there. We have angle ACB, angle ADB, and angle AEB, all intercept arc AB. Now, did you notice something about the name of each one of those angles? Do they have anything in common every single time? Yeah, they had A and B, which was the endpoints of my arc. It makes it slightly easier to pick those out. But the thing is, they all intercept the same arc. So guys, think about this. If they all intercept the same arc, to find the measure of the angles, would I do exactly the same process? It's half the arc. Well, doesn't that automatically make, I mean, to me in my brain, it's like, well, that makes sense. Doesn't that make all of them exactly the same size? So if you know one, do you automatically know the other? You don't have to recalculate. You just know one. Pretty simple, and a lot of ways, very common sense, but it works really, really easy. So guys, does that make sense? If I'm in the same circle and I've inscribed angles that intercept the same arc, they're gonna be the same size. All right, good. Let's try the next example. This time it says, find the measure of angle LJM. So I'm looking for this angle here. Now, the first thing you always look for first is you're like, all right, where's its intercepted arc? Well, here's the intercepted arc. Unfortunately, do I know anything about its measure? No. So I now need to look for something else. Well, what else do you notice when you look at this one? We know that we have angle JKM intercepts the same arc, right? So what's so special about these two angles? Yeah, they're 2 inscribed angles that intercept the arc. They're going to be congruent to each other. So we know the fact the measure of angle LJM is going to be equal to the measure of angle LKM. Then we can just set them equal. So we get 5b minus 7 is equal to 3b. Well, I'm just going to subtract 5b from both sides. So again, negative 7 is equal to a negative 2b. Did you guys get b is equal to 7 over 2? Are we done? No, we got to plug it in, right? So we have the measure of angle LJM is going to be equal to 5 times 7 over 2 minus 7. Right? So we have to get a common denominator, guys. We get 35 over 2 minus 14 over 2. Isn't that 21 over 2? Someone double check my math. Yes. That makes sense? Because you always know it's Monday morning. We all need to double check each other's math, especially mine. Make sense? All right. Awesome. Again, if you're struggling with fractions, would that have been a really good moment to use your calculator on? And use the fraction key? And the answer is absolutely yes. All right. Next one. It says find the measure of angle EDF. So I'm looking for the measure of this angle here. The moment you do that, you should always look for its arc. Do I know the measure of it though? No. So then you're going to go, okay, what other rule do I have? Well, I know that if 2 inscribed angles or more intercept the same arc, they're going to have the same measure. Well, great. If I can move it to the value I want here, you just got to set them equal again. So I get 2x plus 3 is equal to 75 minus 2x. I got 4x is equal to 72. X equals 18. Are you guys with me so far? Yeah. And then I think most of you got it right just ahead of me here. And then we just plug and chug it in. So we got 2 times 18 plus 3. So it'd be 39 degrees. Guys, doable, isn't it? Doable. Notice it's just rules. If you know the rules, you can do it. Know the rules. Okay, now doesn't this one about put you in chaos mode? All right. An art student turns in an abstract design for his art project. Find the measure of angle DBA. I'm looking for this whole angle right here. Right now, it looks like nothing. It looks like I have no idea what it would be. So we start looking for it. Okay, at least we know it intercepts the circle. You guys agree with me that it intersects arc DEA or arc DA, whatever way you decide to choose to name it right there? Is there anything else that's helpful? Yeah, DCA, this one over here, DCA also intercepts the same arc, and we know its measure is how many degrees? 33. So we know the measure of angle DBA, look at this, a lot of work I had to show is 33 degrees. Because that they intercept the same arc. What? Nope. That's what's hard. Makes sense, doesn't it? Pretty easy. All right, let's do another one. This one, guys, I want you to think this is one of the most logical things, and it sounds so complicated compared to what it is. But I want you to look at this right now. Can a semicircle be an arc that's being intercepted by an angle? Okay, so can an inscribed angle intersect a semicircle? Okay, so what's the measure of that angle then? The angle's not 180, it's 180 divided by what? 2. So it's going to be a right angle, correct? What if I redraw the diagram so that it goes like this? What should be my angle yet? 90, because again, if I follow the rule, the vertex is on the circle, so isn't it going to be half its intercepted arc? So what if I drew it here instead? What's your angle going to be? So no matter what, if I intercept a semicircle, if the endpoints of my angle, if you want to think of it like that, are going to be on the semicircle, isn't it always going to be 90? That's what this theorem is telling. Okay, that's all it really is saying. An inscribed angle subtends a semicircle if and only if the angle is a right angle. And to me, that's like, hello, common sense. So when you see problems like this, a lot of times they'll be drawn with diameters in mind, or they'll have them in there. So I'm not lying. This is how simple this is meant to be. I want to find the value of A. Well, A is part of angle WZY. What does WZY, what does it intercept? It intercepts a semicircle because I have a diameter there. So what do we know is the measure of angle WZY? Yeah, because it intercepts it, we know the measure of angle WZY is going to be 90 degrees. That's what our theorem's about. So we literally can just go 5A plus 20 is equal to 90. Solve for A. So I get 5A is equal to 70. Guys, what did you get A to equal? Notice that one is not like a life or death needed theorem, but does it make life easy if you know it? Yeah, because I mean, half of 180 is 90 every single time. It helps calculate these with no problem. And guys, remember, a chord, right, is just a line segment. Both of its endpoints are on a circle, and the diameter is just the longest chord, right? All right, now this one is one that throws people, and this is one I like to test and quiz on. Partly because it means you actually had to memorize it, but I also want you to see the common sense stuff behind it. So let's write the theorem down, then I'm going to explain to you why it works. It says, if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. All right, where in the world did this come from? We'll talk about it in a moment. It says, if a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. Now, let's remember the rules that we've learned so far. if I inscribe a quadrilateral like this, is every one of its angles an inscribed angle? So every one of its angles can be found if you took half of its intercepted arc. Now, I want you right now just to look at A and C. And notice I'm going to draw in a diameter right here just to remind you of that. Do you notice angle A intercepts arc DCB? Angle C intercepts arc what? DAB. So guys, think about this for a moment. I'm going to remark what I just said. Our angle A, or angle DAB, if you want to call it, all right, intercepts arc DCB. Angle DCB intercepts what arc? DAB, correct? Guys, those arcs together add up to what? Hello, my inscribed angles are half the measure, so what's half of 360? Works every single time. So the opposite angles, does everyone understand where I got that from? It's literally because the two intercepted arcs that we work with would add up to 360 to start with. So half of the total is 180. So they're always going to be supplementary to each other. Remember, supplementary means they add up to 180. With me on that? All right. And I want you to know, I think I put like tons of questions on this on homework, so don't yell at me, but I'm pretty positive I had like 5 or 6. I like them so much. So just heads up now, you're going to be liking quadrilaterals on there. So here's an example. It says, find the angle measures of GHJK. So when you look at it, notice on purpose that they give you all 4. If they gave you all 4, could you just add up the angles of the quadrilateral to equal 360 and then just avoid the fact it's in the circle? Instead, though, they're wanting you to use the idea of this, that your opposite angles are supplementary. So really, I'm trying to use the fact that measure of angle J plus the measure of angle G is 180 degrees. So we just plug in our values. So we get 6B plus 20 plus 3B plus 25 is equal to 180 degrees. And then we just start simplifying. So we got 9B plus 45 equals 180. We're going to subtract 45 from both sides. So it's 135. Divide by 9. B is going to equal 15. Can we now start plugging in for our different angles? Now, guys, here's the thing. If you don't love plugging in, do it as little as possible. Because again, what do we know about opposite angles? They're supplementary. So for instance, what if I chose to find the measure of angle G first? So I go here, I got 3 times 15 plus 25. What does that give us for a value? I'm going to move that down just a little bit. Three times 15 is 45, plus 25 gives you what? All right, 70. All right, what is the opposite angle to G? Isn't that J? What's so special about G and J? They're what? Supplementary. Can I just go 180 minus 70 and do 110 degrees? Now, if you wanted to, could you plug and chug it in? And it better be right or we did something wrong. That's a good way of checking yourself. But the same idea, I can find the measure of angle K then. All I have to do is go 10 times 15 minus 69. So it's 150 minus 69, which I believe is 81 degrees. And then to find the measure of angle H, which is the one opposite of it, so they're supplementary, I'm just going to go 180 minus minus 81, and that's going to give me 99 degrees. You see how you don't have to plug and chug in quite so much if you know the rule? All right, you guys try the next one. And yes, I know it's a fraction, but don't panic. Just do it. You're going to be fine. How did you guys do? Good. Did you get it right? It's not bad, is it? Okay, let's do some, and we actually have a little bit of time, so you guys go ahead and do this one real quick. It says find each measure using that funky diagram. Okay, so we have our circle. I'm asking you to find the measure of angle CED and the measure of angle DEA. It shouldn't be, it's just a quick review at the beginning of the lesson, and then we can keep practicing the ones below here. What'd you guys get for CED? Did you guys get 33? All right, what's the measure of arc DEA, guys? It should be 2 times 96, right? So 192 degrees. So the fact is, the first one I needed to know the arc to find the angle, and the next time I had the angle to find the arc. So we went both directions on it. All right, look at the ones below. This is awesome stuff. By the way, those are supposed to be subtraction signs for those. I don't think it printed off real well on your worksheet there from the copy machine. But with this one, what's so special about each one of these guys? Yeah, they're going to be the same thing. They intercept the same arc. So when I look at this, I get 2x squared minus 2 is equal to 10x minus 2. So looking at this, we need to sit there and think, okay, how do I solve for this? The moment you see an x squared and an x, your mind should think probably a factoring problem. Probably a factoring problem. So if you do that, you move everything to the same side. So I'm going to go here, 2x squared, and it ends up being minus 10x is equal to 0. Because what happens to the negative 2's? They simplify out, because if I add 2 to both sides, the negative 2 went away. Now, what's the first thing you should do when you're factoring? Greatest common factor out, right? So I take a GCF out. Don't you take out a 2x? And then what do I get left here with an x minus 5 equals 0. Then you send both equal to 0. I get x is equal to 0, and I get x is equal to 5. Scholars, can I have a 0 for an answer this time? Because if I plug it back in, I get a negative 2 degrees for an angle. Is that a possibility right now? No. So we have what's called that extraneous solution. But for the rest, can I just plug and chug it in? So can I go to just 2 times 5 squared minus 2? Well, that's 50 minus 2, that's 48 degrees. Now, would I expect to be able to do a simple algebra question like that? And the answer is yes. If you panic, that's never a good sign, okay? Take a deep breath and just go, all right, what do I know? What tools do I have in my tool chest in order to solve this? All right, guys, look at the next one. Talk to me. What do you know? It's a 45, 45, 90, right? Because angle G, does it intercept a semicircle? If it intercepts a semicircle, what type of angle does it have to be? A right angle. So if that's the case, we know our acute angles are both 45. So we get 4y minus 7 is equal to 45. So 4y is equal to 52. Is y 13? Yeah. I about said 18. I even had 13 written in my notes. That's not a good sign. All right, so 13. Oh, love this problem down below. Love this problem. I know, I'm so sorry. The blue does not copy well on there. So if you can just trace it a little bit quickly so you can see this one. If you were solving this on your own, what would you do first? What would you solve for first? You'd probably solve for C and D first, right? Because can't we use the idea that opposite angles of an inscribed quadrilateral are going to be supplementary? Does that make sense? So when I do that, I'm right. All right, C is equal to 180 minus 96. I do believe that's 84 degrees. And I get D here is going to be just 180 minus 100, which is 80 degrees. Now, one thing I've learned with working with problems like this, it really does pay to put the angles in after you solve them. Now, here's my question. How in the world am I going to solve for A? Hold on for just a second. How would you solve for A? Can I use the fact that this angle intercepts this whole thing? Guys, what's the measure of this arc from here to here? Right? So can't I solve for A by going 200 minus 99, which is 101? Make sense? Awesome. All right, D, don't worry about it. This was only if we had time, and we did. All right, guys, what should you